at this institution and also in the country. And since I flew in yesterday, I wanted to talk about something perhaps a little easy and a little simple, which is this idea of geometric approaches to these objects called stretched Kostka quasi-polynomials. Just a word for people who do algebraic combinatorics. This is not an associative title. It should be stretched Kostka. Those are the words that you should group together, and not Kostka polynomials. These are not the Kostka polynomials that you may know and love, although I think there is a lot of interesting overlap with that story that is still yet to be looked into. And what we want to do today is look at some geometric approaches to these, and hopefully if we have some time at the end, which I suspect we will, talk about just some kind of upcoming work on how to extend this to related settings. I should also say that this is all joint work with Mark Bassan and Josh Kears, as is the soon-to-come paper, which kind of builds on a lot of these ideas and a lot of our earlier work. So like I say, I want to start with some, what I think of as combinatorics kindergarten, which is the Kostka numbers. So I don't think any of this first bit is going to be new to anyone, but just to at least build some groundwork and set all of our conventions, we want to recall, if I hand you some positive natural number and two partitions, which we're just going to have them have the same number of entries out of convenience for writing things down, then I can associate to these two partitions some number, which is going to be a non-negative integer, which we call the Kostka number. And these things appear everywhere in algebraic combinatorics and representation theory. They pop up, for example, in the representation theory of GLN, which we will use that perspective later on. But if you like, say, symmetric group representations, these are how you decompose permutation modules into irreducible Specht modules, at least in characteristic 0. Among others, right? These pop up all over the place. So one way of defining them is to take the number of semi-standard Young tableau of shape lambda and content mu. So by content, I just mean put in that many copies of each number. So 2 examples and an exercise, right? In my partition 2, 1, so I have that shape. If I want content 1, 1, 1, so I need to put in 1, 1, 1, 2, and 1, 3, then there are 2 ways of doing this where I weakly increase both across the row and down the column. Similar example, if I take 4, 2, and I want to fill it with 2 1s, 2 2s, and 2 3s, then I get 3 ways of doing this. Maintaining this idea that I need to weakly increase across the row and weakly increase, or strictly increase down the column, sorry. And as an exercise, I claim if you do this for 6, 3, and 3, 3, 3, you should get that there are 4 ways to do this. I just did not have space on the slide to put all of them, so we'll leave it as an exercise. But this is the game, right? This is a puzzle that you could introduce to a child, and they would be able to fill in these numbers and count. And it's a nice exercise. So okay, you hand me any 2 partitions, lambda and mu of the same natural number, I can compute, right? We can just write down and try our hand until you fill in all the possible ways. So these numbers are computable. Some good news about them is that if you want to know if they are non-zero, this is a textbook exercise. So knowing that you have at least one way of filling this in is related to whether or not mu is less than or equal to lambda in this dominance order. So for dominance order, we just take all of the partial sums of the partition mu, and that should be less than or equal to all the partial sums for the partition lambda. So actually seeing if these things vanish or not, easy textbook exercise. A bit of bad news is that computing these things is not formulaic. And I'm putting that in quotes just because this is kind of a weak statement. But the feeling is that there is unlikely, in general, to be a nice formula for this Kostka number in what I think of as like nice combinatorial formulas. Parts of the partitions, binomials, factorials, etc. The thing to compare to is that in the case like this first example where mu is just the partition 1, 1, 1. Now these aren't computing just semi-standard Young tableau, these are computing the standard tableau on that shape. And there you do have a very nice formula. It's the hook length formula. So you can write down a formula in terms of factorials, these hook numbers, which are based just on the picture. Nice, easy kind of combinatorial formula that you can see. In general, I don't think we would expect such a nice formula in terms of the parts of lambda, parts of mu, their shapes, kind of factorials. Not a very nice, positive looking thing. But what our goal is, or one possible goal, is what kind of information can you get at all about these Kostka numbers as functions of lambda and mu in a direct way, right? If you move around the space of partitions, this function tends to behave kind of wildly and chaotically. You know, it's very hard to predict what's going to happen as a function in lambda and mu. So the goal is, can you say anything about moving around these lambdas and mu's and what this Kostka number will look like as a function of those? This is a very old and early goal. And there is a result. So I believe it's originally due to Kirillov and Reshtikin when they were looking at fermionic formulas for actual Kostka-Folks polynomials, but this falls out of that formulation, is that if I don't vary lambda and mu arbitrarily, but if I just scale them, so if I take, you know, n lambda and n mu, this is a perfectly reasonable operation because this scaling just preserves the dominance order condition, right? If I have the inequality across those partial sums, then scaling everything in sight by some positive integer also isn't going to break that inequality. So I know if I start with a non-zero Kostka number, scaling them in this way is going to give me, again, some reasonable Kostka number. And it turns out that these things are polynomial in n. And we're going to call this the stretched Kostka polynomial or the stretched Kostka coefficient. So again, stretched Kostka is the thing that groups. And the fact that it is a polynomial is this proposition of Kirillov and Reshtikin. So for example, in our example slide, we started with 2, 1 and 1, 1, 1. And as we scaled those, we saw that in each case, we just added 1. So the stretched Kostka polynomial in this case is just n plus 1. And this is an interesting feature. This turns out to be the polynomial anytime your initial Kostka number is equal to 2. You're actually always going to get n plus 1, but that is not particularly relevant to the goal of today. Okay. So we have a polynomial. The question is, what can we learn about it? You know, what kind of features do these polynomials have? And this was really featured in a lot of work by King, Tolu, and Tomase in like 2004, 2006. They did a very close study of these polynomials, gave a number of conjectures. So the first conjecture is that these stretched Kostka polynomials have positive coefficients. To my knowledge, this is still open. So like trying to get any information about the positivity here is wide open. So anytime I give this talk, I like to advertise this one and say, if you have ideas on this, please let me know. I would love to hear any thoughts about this kind of positivity. A second conjecture, which is now a theorem, it was due to McAllister in 2008, is that, okay, well, we have to parse through a bit of notation. So first, if mu is strictly dominated by lambda. So what I mean by this is that in our dominance order, we allowed for weak inequalities. Here I say, well, each step of the dominance order should be a strict inequality. So all of these partial sums across mu should be strictly smaller than partial sums across lambda. If I also go ahead and set conventions that they had the same number of parts, so these partitions were living in, say, ZR, and if you write out the partition lambda in a slightly different way, you use this kind of common exponent notation. We'll see an example on the next slide, but you should imagine this partition has V1 copies of K1, V2 copies of K2, and Vs copies of Ks. Then the stretched Kostka polynomial has a degree which you can write down very combinatorially just based off of lambda, mu, these exponents, and where they're living. So it has this particular degree. We interpret 1 choose 2 if and when it appears as 0. Does not depend on mu at all. Yeah. It only depends on mu in the sense that you need a strict covering here in dominance order. And so this is one kind of surprising thing, is that you don't really see a lot of mu input here. Okay. R is just the length of these partitions. The number of parts. Yeah. Okay. So, for example, if we start with the example from the very beginning, except now I have made it so that they have the same number of parts, then in fact, if you try to just fill all of the pieces in, you do get that the degree is equal to 1, again, assuming that 1 choose 2 is equal to 0. And we saw that this was a linear polynomial. So this is degree 1. As a slightly larger example, I don't have the actual polynomial down because determining the polynomials can be a bit tricky, especially if you're trying to guess what they are just from lambda and mu. But if you took the partition 4, 2, 2, and a bunch of zeros, and then 3, and then 1, 1, 1, 1, 1, then filling in all of the pieces, you get that the degree of this polynomial should be 6. So this is some degree 6 polynomial. And again, I think the magic here is that you get an explicit formula for the degree based just on very easy to read off data from the partitions. So not particularly hard task.
Is there some priori reason why the degree should be kind of
Kind of. So this is what we will eventually call a kind of primitivity condition. It is morally telling you where the pair lambda and mu live inside of the space of partitions. So it's going to be some cone, and you just want to be in the relative interior. But everything inside of that relative interior ends up having the same behavior. So, and that becomes a little more apparent once we talk about the geometry, and for those who are a little more comfortable with like geometric invariant theory, you don't expect bad behavior to change if you're in the same kind of chambers. Okay. So a few comments. This theorem is really just stated for these pairs where it is strictly dominated, and we call such pairs primitive pairs. But there is a result of Berenstein-Zelevinsky that says, well, actually, for any Kostka number, you can factor it down into a product of Kostka numbers for smaller partitions where each of those pairs is primitive. So this is some kind of reduction rule. So you want to know value for a fixed lambda and mu, and you can reduce it to a lot of smaller lambdas and mu's, where here now you have the primitivity, and because degrees add across products, okay, you can play the same game for the scaled versions as well. And so if you want to know the degree of the stretched Kostka polynomial, you just need to know the degrees of each of its constituent factors. How did McAllister go about proving this? The proof was via Ehrhart theory. So you can build these Kostka polynomials as the Ehrhart functions of certain Gelfand-Tsetlin polytopes based off of lambda and mu. And then the degree of these is going to be exactly the volume. And this is where, again, you kind of see this special property of the primitivity is that the volume of these, if you have this strict covering, doesn't really depend on mu. The only other thing to say here is that from this combinatorial perspective, these Gelfand-Tsetlin polytopes are not typically integer or lattice. Their vertices are not on the lattice. So the fact that this ends up being an honest-to-God polynomial doesn't fall out of this approach. You would only typically expect quasi-polynomiality here. But the fact that you have this polynomiality is a feature, not a bug. This also gives you another toehold into perhaps the difficulty of the positivity conjecture while it's still open. In general, Earhart positivity is a very hard thing to verify. So, so these are, once I fix a partition lambda mu, I can build the Gelfand-Setlin polytope. So these really come from like the representation theory of GLN that give you things like dimensions of weight spaces. Yeah, primitive, it strictly dominates mu, yeah. Mm-hmm. Exactly. Yeah. Yeah, you can always reduce this computation down to primitive pairs. Yes. Yeah. Yeah, as long as you're scaling everything the same way, then this, when you sit down and actually work out how these decompose, it does just pass the factor through. Yeah. Okay. So now I want to move to kind of the representation theoretic interpretation of all of these constructions. So Kostka numbers in representation theory, or at least one application, is that they encode the weight space dimensions for finite dimensional irreducible highest weight, say polynomial representations of the general linear group. And so you can start with, if you're like me and you're interested in representations of reductive or semi-simple groups, if we just start with the notion of irreducible representations and weight spaces, how much of this story can we generalize up? So Leonardo didn't write any of it at all. I took the shortest route and just said, we have the usual suspects in talks like this. We'll fix a semi-simple, and because I really prefer to work with Lie algebras and not have to think too hard about the representation theory, we can assume simply connected, but not particularly harmful if you forget that. And then we fix all of our favorite things. We fix a maximal torus and a Borel. This lets us do things like positive roots and dominant characters. And now to any pair of dominant characters, we'll associate V sub lambda, the irreducible highest weight representation, and then the weight space of weight mu. Again, if you're interested in these weight spaces, there is a textbook non-vanishing, where this dimension is going to be non-zero if and only if lambda minus mu is in the positive part of the root lattice. So at least it is some positive or non-negative combination of positive roots. And we'll write that using kind of the script E less than or equal to, and we'll call this again the dominance order, except now this is a dominance order on the weight lattice. And again, we can see that this condition for non-vanishing is completely stable under scaling. So we can play the same game and ask, well, for non-negative integers n, how does this function of n, where I take the dimension of the n mu weight space inside of the n lambda highest weight representation, how does this function behave as a function of n? And this is the object that we're actually interested in. And so we'll call this the Stretch-Kostka quasi-polynomial associated to G, lambda, and mu. We have a new word here, quasi-polynomial. We should say a little bit about that. So first, if you are working with just SLN or GLN as before, then you can recognize these exactly as our classical Stretch-Kostka polynomials for partitions. But for arbitrary G, these are in general quasi-polynomial, or polynomial on residue classes. So what does that mean? That means that I have some integer d, and I have some collection of d polynomials, such that, well, this function is polynomial on that residue class. This is one way of stating it. You can also talk about it's a polynomial, but the coefficients are themselves functions with a particular period. But I always just think of it as I have a collection of polynomials where on residue classes, that captures this growth. And any integer which satisfies this property we call a period. Periods need not be unique. Right? If you take your favorite polynomial, you could write it as a quasi-polynomial of period 17 if you wished. But it may not be particularly interesting. But these periods are not unique in general. So for example, if you want to sit down and work it out, for G of type B2, if you just take the second fundamental weight and mu to be the 0 weight, then this stretched Kostka quasi-polynomial is the floor function of n on 2. Or perhaps n plus 1 on 2 if I've messed up my indexing somewhere. But not a polynomial, but it's a quasi-polynomial of period 2. So along the even integers, I have a linear polynomial, and along the odd integers, I also have a linear polynomial that will capture these weight spaces, dimensions. So two natural questions based on what we've seen is first, well, what is the degree? And that is, you should really think about what is the maximal degree on the constituents. So a priori, you could have different degrees for each of the different constituent pieces of the quasi-polynomial. But okay, what is the maximal one? And then two, what is a minimal period? So we know that in general, they're not polynomial, but can I predict what the minimal period should be based on G, lambda, and mu? So this was taken up quite recently by Xilian Gao and Yibo Gao. And so in 2024, they proved the following kind of partial answer to the first question. So they say, okay, well, let G be of classical type. So we want to exclude the exceptional groups. Then they have an explicit formula for the degree of these quasi-polynomials, where I have to explain a few of these root systems. We introduced two new subroot systems. The first is just take the span of all of those simple roots alpha I which appear in the difference. So this is like the root system that lambda minus mu is supported on. And then for the second, you just take a subroot system of that where you remember the vanishing of lambda in the fundamental weight basis. And then the rank of the first one. So like the stretched Kostka polynomials, we get a perfectly explicit closed formula, and all it's really depending on is lambda. So that's telling me this d equals 0 part, and then just the support of lambda minus mu. So we again don't see any real dependence on mu here, apart from where it is in the root lattice with relation to lambda. So again, some comments. Their proof is, again, with Ehrhart theory. They replace Gelfand-Zetlin polytopes with the natural thing, which are Bernstein-Zilivinsky polytopes. And because of this very explicit construction, this was what really kept them working with classical types, because they wanted to break down very concretely what these polytopes should look like and be able to compute their volumes. The other thing to say is that they use a very similar reduction to a primitive case or primitive pair case, except now, what do we mean by primitive? You can take G to be a simple group, and you can look at just lambda and mu, where all of the coefficients and their difference are strictly positive. So this, if you wrote down like the primitive condition for partitions, you should land at something very similar. You want lambda minus mu to have full support in the root lattice. This greatly simplifies your degree formula. It's just now the number of positive roots minus the number of positive roots on a much simpler subroot system, just looking at where lambda vanishes. This is the essentially a parabolic root system, minus the rank of the root system of G. Another thing to say is that this particular formula has appeared before. So as a bound on the degree, this has been in the literature for a while. So there's this paper of Day in '98, which used Erhard theory, again, for polytopes coming from Littelmann path model in a much more kind of general setting, but only hit this as a bound. So there's no other place in the literature that we could find where you get actual equalities and when conditions on when you get actual equalities for the degrees. But as a bound, these have been around for a while. So I think the real content of both McAllister's and Gau's results is that you can get exact formulas for these degrees determined by very simple and easy to read off root theoretic data. That, I think, is the key insight of a lot of their work. That's where we're going. Yeah, this is going to be, once you see this, this starts to scream geometry, because this should look like the dimension of a thing. The question is, what is the thing? Yeah. Yes. Yep. Yeah, so that was just the partition case. Yeah, so yeah, this is the general case. Gao and Gao prove it for classical type, but the kind of point of today's talk is that this holds for all types. I do expect it to have non-negative coefficients in each of its constituents, but yeah, trying to prove that is also hard. And I'll say a little bit more about, another way to get around that difficulty perhaps at the end. Okay, so what did we do and how did we attack this? Again, this formula looks very geometric to me. And so the idea is, well, can you attack this geometrically? And so for that, I will give you the briefest sketch of geometric invariant theory you have ever encountered. Geometric invariant theory is a huge topic. It's very useful for doing things like constructing moduli spaces of geometric data. I will use a perhaps different perspective on geometric invariant theory, which is really useful for this kind of problem. So first, say you have a projective variety X and some reductive group acting on it, and you fix a G-linearized line bundle on X, then one application of projective GIT is that you get a translation between a more complicated geometric data, right? So invariant sections, so G invariant sections of this line bundle on X, on an easier geometric object, just a projective variety. So we have an easy geometric object, but complicated data, and we are going to replace it with easy geometric data, which is just honest-to-God global sections of a line bundle, but on a harder geometric object, which is these GIT quotients. So for the purposes of this talk, this is what geometric invariant theory is doing for us. It's a translation between swapping out difficult geometric data with easier geometric data up to the cost of having to deal with more complicated geometric objects that you're living on. So what is the projective GIT quotient? It's going to be you take your line bundle and you take as many powers as you want, and I want to look at just G invariant sections on a particular open subset of semi-stable points. So this are determined by L. I won't go through exactly what these semi-stable points are, how you determine them by L, but the takeaway should be is there is a very nice open subset, and for any of this to really be useful, you should assume that it's not empty, where I can look at the invariant sections, and when I take the Proj construction of that, then this is going to be what I should think of as some kind of quotient by G of this variety X. And in the nicest cases, if you have stable points, not just semi-stable points, but a more refined stable points, then computing the dimension of this thing is very easy. So it will be a projective variety of dimension exactly dim x minus dim g. So these stable points I think of as these quotients now have actual like geometric meaning. This feels like a naive kind of geometric quotient fact, that the dimensions should just be the difference. But in general, this is a bound. Right? You always have at most this dimension, but hopefully when you're lucky, you get exactly that. Okay. A minor inconvenience about this construction is that we like to think of it as a passage between this invariant sections on X and sections on the quotient. You may not have such a line bundle. So there may not be a line bundle L hat on the GIT quotient that has global sections exactly the invariant global sections of X, or of the line bundle L on X. So this is an inconvenient fact, but it's not too hard to get around. It depends just on what kind of geometric object downstairs you're okay with. So first is, if you just take the quotient map from the semi-stable locus down to the GIT quotient, then if you just replace L hat with the invariant push forward of L, then this isomorphism holds. The problem is that what you have downstairs is no longer a line bundle, but it's like the next best thing. It's a rank 1 reflexive sheaf. So replacing this left-hand side with this statement, the theorem is true, or this isomorphism holds. If you really want there to be a line bundle downstairs, then you don't get to pick L, but some power of L. So we say that some power of L descends. So there is a line bundle downstairs and a positive integer, such that if I pull back the line bundle downstairs, I get the Dth tensor power of L upstairs on the semi-simple locus. And then, if you want to compare global sections, you can relate the line bundle downstairs to maybe not L, but some power of it. So, okay, two easy ways to get around this minor inconvenience. Depending on what you like, we will actually end up using both pieces. But I think this question of descent and what line bundles descend to the GIT quotient is quite interesting. That is going to be one of the takeaways, is that any such power D that descends is a period of one of these quasi-polynomials. Yeah. So Bouchek worked in the case of like tensor products. Kumar has the list, what I call the descent lattice, that tells you exactly what these Ds are in the case that mu is equal to 0. So there you can write down powers that do descend. It's still not known that those are like the minimal periods. So a priori, you could have a smaller period than those. I think that that is probably false. I think for mu equals 0, Kumar's list is probably like the list of minimal periods. I don't think it really does. Mm-hmm. Right. Yeah. So I don't know enough about the GIT stack perspective. I don't know if it would get you much more. Yeah, I can't say much about that. So yeah, so we will set up, so this is still very general. This is general X's and G's and L's. But in our case, which I think might happen on the next slide, we're interested in this side. Yeah. Exactly. That's exactly what's going to happen. You know how to identify. I don't know if you know how to compute. Computing is a different kind of story. Yes, but I don't know if in any of these constructions, if this scaling is very natural. Right. So how do we make this machinery work for our case? So a twist on Borel-Vey tells us that actually I can compute these stretch Kostka quasi-polynomials as the dimensions of some global sections on a flag variety of some aligned bundle where I'm now taking T invariants. So what is this setup? Well, I want to take the standard parabolic, which is determined by lambda, and then I take the usual line bundle L lambda, which gives us the highest weight representation, or its dual, depending on how you set things up. And then I just want to twist its T linearization by a character mean. So setting all of this up carefully, I can now look at the T invariance of this powers of this line bundle on the flag variety, and this will give me this function. So the goal has to become, how do you compute such things? And once you have this formulation, the relationship to GIT is kind of screaming at us. How do we do? We go about this using both perspectives on how to get around the problematic non-isomorphism. Is that first, pick any power D so that L tensor D descends to some line bundle on the GIT quotient. So take your favorite one that works. And then for everything else, okay, I can at least push forward a power of L for k between 0 and the power that descended to some rank 1 reflexive sheaf downstairs. And then combining all of that together, you get that this space of T invariants is exactly this space of global sections on the GIT quotient. And now we're in a setting where I've got a projective variety, I've got some coherent sheaf with powers of a line bundle that I'm interested in. You can apply asymptotic Riemann-Roch. And this is going to tell you, okay, well, for each fixed k, this dimension is going to be polynomial in n, and you can collect all of those together for all of these k's to build you a quasi-polynomial structure on this function of period d. Yeah, so because of Borel-Vey and how all of this passes through, we do have higher cohomology vanishing to know that this works. Yeah. Exactly. Yeah. Yeah. Okay. Right. Okay, so when I say asymptotic Riemann-Roch, I mean it in the sense of, this is how Wikipedia says it, which is, if you have a projective variety, a coherent sheaf, and powers of some, say, ample line bundle, then the function of n goes to the dimension of such a dimension of global sections is polynomial. Or really, you may have to worry about Euler characteristic and eventual polynomiality. In this case, everything is so nice that you end up with a polynomial from the get-go. Now, in this setting, if I want to get the entire stretched weight space dimensions, well, each of these is going to depend on k, because I don't have that my line bundle descended on the nose. If it did, then I know that this thing would be polynomial. So here I correct that by saying, okay, well, scale the part that does descend, and then for every fixed part that doesn't, just take the push forward to some rank 1 reflexive sheaf downstairs. And now this is polynomial for K mod D. And I can collect all of those together. D here is just any power of the line bundle that descends. I don't know it, but one exists. Small n is saying now I'm scaling here. So capital N should really be like dn plus k. Yeah. So, right, so what is another actual takeaway of Riemann Roch is that when you have this, you know that this is going to be polynomial for a fixed k, so I can build together a quasi-polynomial, and the degree of this polynomial is only really going to depend on the dimension of the support of f, or in this case, because it will be supported everywhere, I just need to know the dimension of my variety. So if you can compute the dimension of these GIT quotients, then you know automatically the degree of these polynomials. And that is the theorem. So in the case where G is simple and you have lambda and mu, two dominant integral weights, which are primitive, so their difference has full support, then the GIT quotient has dimension exactly just dimension of the flag variety minus the dimension of the torus, which recovers on the nose the degree formula that you get in Gao and Gao's work. So the corollary is that, well, for a simple G in primitive pairs, these stretched Kostka quasi-polynomials do have exactly this degree. And that suffices, again, by this factorization result. Using the same kind of results of Berenstein-Zelevinsky, any of these stretched Kostka quasi-polynomials can be factored into primitive ones. So you're reducing weight space dimensions down to products of weight space dimensions for like simple levies. So a very kind of common reduction step. Say it again. This L, so this is the line bundle that I want to take. So this is this particular line bundle. So everything here, it depends on L in the sense of as long as lambda and mu are primitive, then the degree doesn't depend on like lambda and mu apart from this factor. So this is still determined by lambda. So there's L dependence there. The thing that really disappears in the dependence is the mu term. You don't really have dependence on mu as long as lambda and mu are not too close together in dominance order. So, I mean, the only other kind of comment to say is that the GIT story doesn't matter at all about simple and primitive, but the dimension count is just much nicer if you make those assumptions. And so computing this dimension is much more straightforward than trying to do it in the general semi-simple case without restrictions on lambda and mu. I think one could write it down, but using this factorization into primitive pairs by Berenstein-Zelevinsky really simplifies our life. Okay, so the last few things that I want to say are just some open questions. The first, does it have positive coefficients? Conjecturally, yes. I mean, I'm making that conjecture basically now. I don't think anyone has ever really written it down. But in our computational examples, so we have a lot of examples in type B, C, D, F, G. You see very interesting patterns in the coefficients. So for example, like it's not so bad based on asymptotic Riemann Roch to know that like all of the parts of your quasi-polynomial have the same degree and have the same leading coefficient. And they often share a lot of coefficients. Like a lot of the coefficients tend to be shared across each of your constituents. I don't have a good reason to know why that should be the case, but everything that we see positivity. So again, the combinatorial incarnation is Ehrhart positivity of Bernstein-Zelivinsky polytopes, Gelfand-Cetlin polytopes. As a geometric incarnation is, could you actually not just use asymptotic Riemann-Roch to know about how these things grow, but if you really sat down and tried to compute just Riemann-Roch on the GIT quotient for these line bundles, is there kind of any apparent positivity happening in those computations? This is something that I think would be very interesting to explore. It's not something that we have looked at. The other question is, what are these minimal periods? So as I said, polynomiality in type A is combinatorially surprising. You don't expect often, if your polytopes don't have lattice vertices, to be polynomial. What is kind of geometrically obvious, although still unproven, is that all of these line bundles do actually descend to the GIT quotient. So if mu is equal to 0, that does go back to Kumar. But for other mu, we have tried to work out very briefly what these descent conditions should be. Didn't make a lot of progress, and we moved on to other things after a couple days, but I think that is something that can be worked out, is based on lambda and mu, what are the descent conditions? Those give you a potential minimal period, and I think that the geometry is very much suggesting that those should probably be the minimal periods. So, for example, in the mu equals 0 case, type A is a polynomial. Classical types have period at most 2, so they're either polynomial or just polynomial mod 2. And then for exceptional types, it's a finite list, and I think those numbers should be the same across all lambda and mu, at least primitive. So we have like what we called an open or a soft question in the paper on how to actually determine these D, and all of our computational examples match those predictions, but we don't actually have a proof that these are, in fact, powers that descend to the GIT quotient. Finally, because of the theme, what about Schubert varieties, right? Can you do this whole story again? And you can. So if you're interested not just in irreducible representations, but if you're interested in de Mesure modules, then you could ask the same kind of game, how do weight multiplicities for de Mesure modules grow? Here, we won't necessarily make the restriction that mu is dominant. Mu could be any weight in the de Mesure module. So again, geometrically, or again by this work of Day in '98, these are quasi-polynomial. There are very natural upper bounds on the degree, and those upper bounds are also very much kind of clear from the GIT perspective as well. So the question is, how do you get equality, which I think is the important part of this whole story. How do you get the exact formula? You need some notion of this primitive pairs condition. So all of the exact equalities were for these primitive ones. So the question is, what are the primitive ones, and do you get a reduction rule to replace a weight space computation for lambda mu w to a smaller one, particularly of a levy? And the only thing I'll say is that we have such a reduction rule for very nice predictable levies. So the reduction rule is going to be a topic of some forthcoming work with Mark Lasson and Josh Kears. But then once you have that, you can run this machinery again with these new kinds of primitive pairs and get less combinatorially explicit, but still explicit formulas for the degrees in the de Mesure module case. And I'll stop there.